Okay, so today we're going to talk about initial value problems with the spring mass system. And this part 1 on the video, we'll talk about undamped and the motion equation. So free undamped motion for simple harmonic. We're going to start with Hooke's law. And Hooke's law basically gives an equation for the spring constant, depending on how tight the spring is. So the formula is F equals Ks, where F is the force, K is the spring constant, and S is the length of the spring. So let's do an example. Okay, so a mass weighing 6 pounds stretches a spring 3 inches. We want to find the spring constant. So the force is going to be the weight, the 6 pounds. And we are going to convert to feet. So S is 3 inches, which is 3/12 of a foot. So S is 1/4 of a foot. So F equals Ks. 6 equals K times 1 foot feet. 6 pounds. Let's keep the units in there so we can see what the units of K are. Solving for K, I'll just multiply both sides by 4, divide by a foot, and K is 24 pound-foot. That's our spring constant. Okay, so now I'm going to talk a little bit of physics here. So Newton's second law is basically force equals ma, just common formula. We also have weight equals mass times gravity. So let's look at a spring that's hanging, just a natural, that's the length. And this is our unstretched spring. So the length of the spring is L now. Now, what we're going to do is we're going to take that string and we are going to hang a mass on it. So I've done a little marker here, and we've got L and then S. So L is from here to here, and S is the rest of it. So we can see that S is the additional length that the spring was stretched when the mass is on it. So I'd like to talk about equilibrium. So our Ks, which is our force, our spring force, is going to equal to mg, which is our weight, because it's not moving. So this is our weight, and that weight goes down, and this is our force that goes up. So the sum of the forces on an object in equilibrium is 0. In this case, we've got the sum of F equaling to mg minus Ks. mg minus Ks is equal to 0. You can see that it's equal to 0. Okay. Of course, we can do it either way, subtract it either way, but I do want us, as we can see here, we have decided, when you look at our mass, mg is down and Ks is up, and this is going to be our positive going down, and this is our negative going up. So the sum of the forces acting on this mass that's not moving is 0. That's the picture that represents what we're doing. So now what we're going to do, so remember force equals ma, weight equals mg, and our L from above is our length of the spring, or S is the amount of elongation at rest, how much more it's stretched when you put on the mass, and this is at no initial force. Little m is mass, and it's usually measured in slugs, kilogram, or gram. W is our weight, and our g is our acceleration, free falling. Or we can use 32 feet per second squared. And a is our acceleration of motion. And another thing we can call it is d squared y. Well, not y, we'll use d squared x in terms of time squared. So now we're going to have a spring, it's L, and we have S, which is what the mass pulls it, and we're going to have X, which is how much more we're going to pull it down. And there's my mass. Now, this can also be, if we pull it down, this is pull down, L plus S plus X, because it's positive. If we're pushing it up, then we get S minus X, because X will be pushed up. Remember, the negative direction is going to be up, and that's my length. Remember, this is when X is going up, which is negative. So this is stretched harmonic motion. And we have, let's look at the picture. If we look at here, we can understand it better. Sum of F is equal to mg minus k. And instead of S, it's going to be S plus X, which is ma. So force is ma. Let's write this equation out just on the right. Mg minus, I'm going to distribute this, Ks minus Kx is equal to ma. And remember, mg minus Ks is 0. So this is basically 0, equilibrium. It's from equilibrium. So we have minus Kx is equal to ma, or minus Kx equals m. A is acceleration, d squared x dt squared. And we can add Kx to the other side. 0 equals m d squared x dt squared plus Kx. And this is our ma plus our Hooke's law. Now, the way I like to draw this, again, we had, before we pushed it, when it was just in equilibrium, we had Ks is one force, the other force in the opposite direction is mg. That was from above, but now when we stretch it, we have Ks plus x. Okay? So this. And this actually can get cleaned up when you have Ks plus Kx, still just distributing that. It's a sum of it, so we can look at it as they're both coming out like that. Two forces going up. And then we have mg here, but Ks and mg are equal. So the sum of the forces acting is Kx. And that's how we get that. Okay, so this is our equation in general for undamped. We have md squared x dt squared plus Kx equals 0. Again, where m is our mass, K is our Hooke's spring constant. And when we go to solve this, so we're actually going to call, you'll see why in a few minutes, we're going to call omega squared equal to K over m, where if we take the square root, omega is equal to the square root of K over m. Omega is angular velocity, and it's measured in rad per second, radians per second, angle per second. So again, that is the angular velocity that you might have studied in trig or physics. it's the same one. Pretty cool, actually. So now let's solve this equation using omega. It's a constant coefficient. So x equals e to the RT. X prime equals so we get two imaginary roots, which means my fundamental set so here's a note. So in order to have a unique solution, we do need two initial conditions because it is a second order DE. And so our first one, x of 0, is our initial condition at t equals 0, is our initial displacement from the equilibrium. So how far away is the distance from equilibrium? Again, it could be, if it's pulled down, it's positive, it's pulled up, it's negative. And our second one, that's, so we have distance, and then the derivative of is velocity. So that's our initial velocity. And again, same thing, plus is down, minus is up. Okay, that's for both. And just so we're clear, to dampen, you can think of like you want to dampen the noise, for example. If you have a cymbals and you crash it, well, you can dampen it by touching it, okay, because that slows it down or stops it, either one. So to dampen means to stop or eventually stop, slow it down. And since it's not getting slowed down, it's harmonic. It's undamped. So to be honest, though, that's every time we have undamped, that's going to be your solution every single time. We will do an example here and look at an equivalent motion equation of it so we can understand what's happening. But mostly it's more useful to have an equation that's dampened or a driving force. So we'll be doing both in the next videos. Just some other tidbits. One slug equals, not equals, it's actually approximate. It's approximate 32 pounds. One slug, the units of a slug, it's just a bunch of them, that's why we call it a slug. It's 1 pound-foot divided by acceleration, feet per second squared. And slug measures mass, as you can see there. Okay, let's do an example. Okay, here's our first problem. So we have a mass weighing 4 pounds, and it stretches a spring 3 inches at equilibrium. At time equals 0, the mass is raised 6 inches, so it's pushed up, and released with a downward velocity of 2 feet per second. So we want to find the equation of the free undamped motion. Okay, so this is undamped motion, so it's just the formula we just used. M d squared x, the acceleration, plus kx equals 0. And this is our MA, and this is our hooks. And also at t equals 0, the mass is raised 6 inches. Raised is up 6 inches. But remember, that's going to be negative. So we have x of 0 is minus 6 inches. But we do want to convert it to feet. There's 12 inches in 1 foot. So the inches cancel. Inches cancel, and we get minus 1/2 the foot. And x prime of 0, the initial velocity, released with a downward velocity. It's released at time equals 0. It's released, time equals 0, with a downward velocity of 2 feet per second. Equals 2 feet per second. And it's downward, so it is positive. Let's box these, because we'll come back to these after we solve for equation. Okay, so first let's find k. And it's, what's Hooke's law? Again, it's F equals KS is our Hooke's law. We have S is, it's stretched 3 inches. But again, we do need it to be in feet, so it's 12 inches per 1 foot. Cancels. Equals a force. The force is going to be 4 pounds because that's the weight. So 4 pounds equals 16 pounds per foot equals my K, so 16. And our mass, well, we have our weight, which is 4 pounds equals mg. Our weight is 4 pounds. We're looking for m. And our g, again, there's 2 g's we can use. We're using the one with the feet. So that would be 32 feet per second squared. So our mass is 1/8 pounds per feet second squared. That looks like it's the units for 1/8 of a slug. Equals my m. Okay, plug it in to this equation. M is 1/8 d squared x over dt squared plus k is 16x equals 0. Clear out our front. D squared x dt squared. I'm going to multiply 128x. So this is my k divided by m. My omega squared is 128, which we'll use later. Omega is the square root of 128. So perfect squared in there. 64 times 2, it looks like 8 root 2. But we can just solve this normally without regards to omega. So we're going to use this to solve because it's constant coefficients. So this is our x double prime. Factor that out. And again, square root of 128 is 8 root 2. So our fundamental set is cosine of 8 root 2 times t sine over the same angle. So we have our equation, general equation. And we have our 2 initial conditions, x of 0 is equal to negative 1/2, and x prime of 0, I forgot, is 2 feet per second. So these two, we already wrote them down. So plug those in to find our constants. First one, or we could go ahead and just take the derivative and plug it into both. Oh, sorry, it's times. Derivative, not integral. So chain rule is how I got that. Looks like I need a little bit more room here. Okay, so I took the derivative, now I'll plug them both in. So in our first equation, we'll plug this in. So -1/2 equals cosine of 0 is 1. So we found our C1. And our second derivative, plug this in. So 2, we get 0 there, and then 8 root 2 times C2. Divide by 8 root 2, divide by 8 root 2, so C2. And if we want to rationalize it, maybe it'll turn out a little nicer. So C1 equals -1/2, C2 equals. So x of t, our particular solution, is our solution. So again, this equation pretty much describes the motion. So we're going to convert, we'll do it in general first, and then we'll come back and do this problem. We're going to convert to x of t equals a sine of omega t plus v. So as you notice, we already have found omega. Okay, so that was our angular velocity, and it's in this formula. So we've already found a piece of it. We just have to find the amplitude, and we have to find phi, which is and we have to find phi, which is our phase shift. Phase angle, I should call it. So A is my amplitude, and phi is my phase angle. Okay, so in general, this is how we do this. There's a formula that maybe you've seen before, but maybe not. You probably don't have it memorized, but that's okay. The easier equations that come out of this are what we'll be using to convert in the future. So this is equal to, so remember we have omega t in our equation. Basically, we're going to convert our function to this, and just so we can equate, what you see here is the sine, the sum of angles formula. So A will be in the front of both of them. It'll get distributed. And basically it starts off with the sine of that first angle. So it first starts off with the sine of omega t, and then it pairs with the cosine of phi. And sine is the same sign. A gets distributed, and then we flip. It's the cosine of omega t, sine of phi. Okay, so there's that equation. Now what we need to do is equate this equation with the one that we got. I'm actually going to write this one first. I'm just going to flip-flop these. So this is equal to A, you'll see why in a second, cosine of omega t sine of phi plus A sine of wt cosine of phi. Now remember, now I think you can maybe see, we have this and we have this from our other equation from above, right? So let me write my other equation in general, my other general equation. So we have C1 cosine of omega t plus C2 sine of omega t. So what this means is, maybe I should flip-flop these two, just so you can see it ultra clear. So this can be rearranged. It's A times this. So I'm going to do A sine of phi cosine of omega t plus A cosine of phi, sine of omega t. Okay, now do we see it? This is this, which means, whoops, I went a little far on that one. Which means, let's do it in green. This is this is this. So we just found two equations that we can write out. So my C1 is a sine of phi, and my C2 is a cosine of phi. Okay? Now, if we want to, I'm just going to draw this picture in quadrant 1, but remember, phi does not have to be less than 90 or less than pi over 2. But let's just draw this here. We draw phi. We basically have cosine of phi equals C2 over A. We have it as a ratio. This one, sine of phi equals C1 over A. So A is my hypotenuse. C1 is there, C2 is there, and those are our formulas actually. To find phi, sine of phi equals C1 over A, and cosine of phi equals C2 over A. So what is A? We'll look at our picture here. A squared plus, whoops, not plus, it's a right triangle. So A squared equals C1 squared plus C2 squared. So we can solve for A, it's the square root of C1 squared plus C2 squared. So it's coming together. Phi, take the inverse of any of them, or we can do, using C1 and C2 would be the best really, because we already have C1, C2, so phi is the tan inverse using our picture. Tan inverse of C1 over C2. C1 being the one in front of cosine, remember? So that does matter. But also, our note, be careful, because phi can be in any quadrant. So look out for that. You can figure out what quadrant it is by these two equations, though. If they're both positive, we're in quadrant 1. If they're both negative, we're in quadrant 2, and so forth. Right? So cosine sine is positive, positive. Negative, negative in quadrant 3. If it's positive, negative to the right, down, cosine sine, and so forth. This would be negative, positive, cosine sine. They're the same ordered pairs as xy, the signs of xy, if you haven't noticed. Okay, now let's go ahead and just convert our last example. So let me write out our equation. We had C1 equals negative 1/2. So let me write the equation. So x of t equals minus 1/2 cosine of 8 root 2 t plus root 2 over 8 sine 8 root 2 t. So C1 is negative 1/2. We'd already found this and written this out. C2 is square root of 2 over 8. So we can find A is the square root of C1 squared plus C2 squared, which is the square root of 1/4 plus 2 over 64. And use the calculator, because I wouldn't have to simplify it if I needed to. 0.53 feet, or if you want to look at it in inches, convert that to 6.4 inches. Okay, so let's look at phi. We have cosine of phi equals C2 over A divided by, we need feet, 0.53, which which is approximately 0.333. Sine of phi equals C1 over A. C1 was negative 1/2 over 0.53, which is negative 0.9428. So you see one of them is negative, cosine's positive, sine is negative. So we are in quadrant 4. So let's do tan inverse of 1 over C2. That's my phi. Is equal to so you punch that into a calculator and you get approximately negative 1.234, which is in quadrant 4. It's in radian measure, remember. Make sure you're in radian. You can't have a degree. Doesn't make sense in this class. Now, just a few more definitions before I sign off here. T, which is a period, is going to be T equals 2 pi divided by omega. And if you just look at our units, just so that they make sense, 2 pi, it's 2 pi radians divided by radian. Omega is radian per second. So basically the units, the rads cancel. It's 1 over 1 per seconds. So our units do work out. So that's our definition for period. Frequency. Which we call F. So basically frequency equals 1 over T, the one that we just found. So our units would just be the reciprocal of that, or 1 over a second. So it's frequency per second. How many cycles per second? Now remember our amplitude on this last problem. Our amplitude was 0.53. That was feet. So that's going to be our max. Our max when x is greater than 0 is going to be 0.53. And our minimum when x is less than 0 is going to be negative 0.53. That's what, when you're graphing a sine, no matter what the max is, your amplitude, your negative a, right? It's the height. Okay, that's it for today. Next video on this section, I will be covering damped motion and driving force. Okay, have a good day.